once we know what inductive and deductive reasoning are, their definitions, their purposes, some of the differences, we can start to examine the connections between these and see how they work together. So both have their place in mathematical reasoning in helping us create new mathematics, make discoveries, determine how we know what we know. So both are valuable, and we just need to see the connections between these two. So as a reminder, inductive reasoning usually concerns itself with examples to begin with, or maybe smaller things or more specific things, and it works towards some sort of a general conclusion, or we would often call that a conjecture. Deductive reasoning, on the other hand, begins with things that we already know and then works to apply that knowledge into perhaps specific situations or just to a variety of different examples. So let's explore a few examples that make this a little bit more concrete. So let's start by inductively determining the digit in the ones place of 3 to the 99th power. Now I know the writing here is a bit blurry because of the video quality, but you do have a worksheet and you should follow along and take your own notes to go along with this. Alright, so let's start with, we've got 3 to the 99th power, and we want to try to find the digit in just the ones place. So quick review, a number like 456, the 6 is the number that's in the ones place. So we don't actually need to know the entire value of 3 to the 99th. I just need to know what its last digit is. Well, how would we do this inductively? Well, let's begin by looking at examples and try to come up with some sort of a pattern. So I'm going to guide or direct us to a specific type of examples that will be helpful. So let's begin with the different powers of 3. So maybe we start with 3 to the first, and that's 3. And then 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. 3 to the fifth is 243. And 3 to the sixth is 729, and so forth. Right, so I'll let you discuss and see if you can find a pattern and use that pattern to make a guess as to what the digit in the ones place would be. So here's my hint. This is a pretty big hint, but I would look at just the ones digits. Right, so that would be 3 and 9, since those are just single digit numbers, and then 7 and then 1, and then 3 and then 9. And if I were you, I would probably write out a few more examples just so that we can see some sort of pattern start to emerge. So what is 3 to the 7th? What is 3 to the 8th? 3 to the 9th? And so forth. And then see if you can use that information to make a prediction about 3 to the 99th. Now you might be wondering, well why couldn't we just type that into a calculator and determine the exact value and then see what that ones place is? Okay, well, first of all, we can, but that would just not be inductive reasoning. That would maybe be more deductive reasoning, because we would be operating under a few premises, one of which would be that calculators are accurate, and just our knowledge about what the ones place is, and then observation. Basically, we would be working from information that we definitely know for certain, and we would conclude for certain what that last digit in the ones place would be. Now I encourage you to try this too, and I think what you're going to find probably on most of the calculators that you're using, if you have a scientific one for the course or a cell phone calculator, you can enter this in. So you would do, you can do 3 to the 99th. You may have like a little caret symbol on your calculator. You may have a key that's like x to the y, so you would type 3, then that key, and then 99. Yours may be similarly like y to the x, or maybe a to the b, so something like that. That's going to be the exponent key. And so you would enter that, and then that would tell you the value of that number. All right? So this means, 3 times 3 times 3 times 3, dot, 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 etc., okay, times itself 99 different times. Now, I think that most of your calculators probably won't display this exact value. You're probably going to see it in scientific notation. So for example, I have an iPhone and mine looks like this, and when I enter this in, I get 1.717, a bunch of other numbers, and then I see E47. Okay, and you may see something similar, maybe a capital E, if you're using some sort of scientific calculator. Okay, but you're probably not going to see the whole thing, because if you remember, this E47, right, that actually means times 10 to the 47th power, or in other words, it means we would need to move this decimal place 47 places to the right until we reach the end of that number, until we get to that ones digit. Okay, so this is a rounded number here. This 7, I don't even know if that actually is the number, or if there was something after that rounded a 6 up to a 7. But in any case, I definitely don't have the other numbers that follow after that. I can't see all 47 digits. However, there is a neat way to see all of these, and we just need a more powerful calculator. So if you wanted to do it this way, you could go to the website. It's Wolfram. Let me write this very clearly. wolframalpha.com. Wolframalpha. Okay, all one thing there, .com. And if you just enter in, all right, this notation, 3, and then the little caret symbol, and then 99, and then you hit enter, that will actually show you the entire value of the number, and you can look through that and see what that last digit in the ones place is. All right, so you may want to try this inductively first, try to see if you can find a pattern and predict the digit in the ones place, and then go on and maybe use that tool, that calculator, and you can actually see if your prediction was correct. Here's another example of inductive and deductive reasoning working together. So we're returning to some of the number patterns that you explored back when you did an inductive worksheet. And so you've already done this first part. You thought of a number. I'm going to go with maybe 3. You multiplied that number by 2, added 6, and divided the result by 2, and then finally subtracted the original number. And if you remember, it turns out that no matter what number you start with, you always, hopefully, ended up with a 3 as an answer. Okay, so if I had chosen maybe a 5 here, let's just do one more. So if you start with a 5 and double it, add 6, divide by 2, and then subtract the original number 5, you always end up with a 3. Right? So inductive reasoning is this whole process of looking at examples. So you would look at the example of what happens when you start with 5, the example of what happens when you start with 3, the example when you start with 8. Maybe you got creative and started with a decimal or a fraction or something like square root 3. And you would use all of those examples to try to make a conjecture, a general conjecture about the pattern starting with any given number. Right? So your conjecture would say something like, maybe if the arithmetic above is performed on any number, the result is always 3. Okay? Now we could, this is inductive reasoning, so our end conjecture here is more general. Now we could use deductive reasoning to do a couple different things. First of all, I could use deductive reasoning to then start with that statement as a premise and then make specific conclusions. So I might say, well, I'm going to start with the number 103.52, and I'm guessing that none of you chose that number as your starting number, but using my premise here, this if-then statement, then my secondary premise would be choosing this number 103.52 and performing that arithmetic, and then my conclusion would be that the result in this case is also going to be 3. So that's one option for using deductive reasoning. A second option would be to use deductive reasoning to prove this conjecture. So here I would just start with any known information, and I would want to just create a chain of true statements, or perhaps I should say valid instead, so a chain of statements that all depend on each other that lead me to that pattern in general. So you may be familiar with working with numbers in general, but what you would normally do here is use some sort of variable just so that we're not relying on any specific number. So let's start with the number x, and we're going to let x represent any number at all, fraction, decimal, real, not real, we'll talk about those later, and let's perform the arithmetic on x. Okay, so I'll use arrows here rather than equal signs because we can see that as we move from one step to the next, they're not equal. Like here, 5 doesn't equal 10, but I'm just showing that I'm moving from one number to the next. All right, so there's my number x. Multiply that number by 2. So a little bit of a review of algebra here. We would express that 2x. Then add 6. So that would just be written 2x plus 6. And then divide the result by 2. All right, so we have two terms here, 2x and 6, and you might remember that when we divide something like that by 2, both of those terms get divided by 2. All right, so 2x divided by 2 would become 1x, and then 6 divided by 2 would become 3. So that's going to become x plus 3. And then finally subtract the original number. All right, well, that's x plus 3, and then subtract, well, what is the original number? I don't have something specific to work with in this case, I just have the variable x, so that's what I'm going to subtract. And then finally x plus 3 minus x, that's the two x's will cancel, x minus x is 0, and then that leads us to just 3. All right, so this is deductive because first of all, I'm starting with a general number, x, I haven't assumed anything about it, and then I'm using known information. I'm using rules from algebra and the rules of arithmetic to write the steps that are done to x, and then I end up with this result of 3. So this proves it in all cases. Now I don't need to wonder what would happen. For example, if we started with pi, I know that following these steps will always lead to a result of 3. There's a third example, so I will leave this for you to try on your own and discuss, but you've already done this first part. You've thought of a number, followed these other arithmetic steps, and you should have a pretty good idea of what the result always turns out to be. So first of all, use inductive reasoning to make a conjecture about that general pattern. Okay, so what is the result all the time? And then deductively prove it. So try to start with an x, and then follow all of those arithmetic steps, and then try to show that you end up with whatever you think that you do. Here's another practice example for you, classifying arguments as deductive or inductive. All right, so go back and look through the definitions of inductive and deductive reasoning and try to decide what type of premises we're using here. So I would probably even underline in these sentences what are the premises and what part is the conclusion. So for example, in number 1, the last 6 times we played our arch rival in football, we won. So, and then that keyword like so or then or therefore, those are keywords that indicate that a conclusion follows. Right, so everything before that is going to be a premise, and then everything after that is going to be the conclusion. All right, so look at those two things and see if these seem to be inductive or deductive. So let's put the pieces together. How do inductive and deductive reasoning work together? Well, we often begin with examples or observations, especially if we are observing the world around us and trying to determine new mathematical things or maybe non-mathematical things. But we'll stick with mathematical reasoning for this example. All right, so you would start with examples and then you would use inductive reasoning once you look at those examples and maybe see a pattern, to make some sort of a general conclusion. And because the conclusion isn't necessarily true or false or valid or invalid at this point, it's just more or less likely depending on the number of examples and how good they are. I'm just going to call this a conjecture instead of a conclusion. So inductive works from those examples or observations to some sort of a general conjecture. Now we have a few options at this point. We might want to then go on to decide whether or not that conjecture is true or false, or reflects the reality around us. All right. So one option is to try to disprove that conjecture and show that, well, actually while that seemed likely, it's not actually the case all the time. So what we would need is some sort of a counterexample that disproves that. So if we could come up with an example of a situation where that conjecture is not true, then we would have disproved the conjecture. Okay. And then we would sort of start all over again, and we would go from there back up to discovering other examples and maybe coming up with a better conjecture that's more accurate. On the other hand, if we suspect that the conjecture is likely, then what we would want to do is to try to prove it, and we would do that by bringing in other known information to do that proof. So here we would use deductive reasoning to work towards a proof of that statement, and then we would know that that's true in general. And then once you've done that, then you can go from there, and once that's proven, then you can use that conjecture as your premise, okay, once it's proven, and go on to conclude other information. So you make new connections and discover new things based on that conjecture, which is now proven. And that's done deductively as well. All right, so there's still one thing on this little diagram that we have yet to talk about, and that's the idea of a counterexample. So counterexamples are specific examples that contradict a conjecture and thus show that it is false. All right, so here's a tip: when you're looking for a counterexample, you want to think of an example that meets all of the conditions of the conjecture, but for which the conclusion is false. So let's say that our conjecture is that the name in English of every month contains either the letter Y or the letter R. So maybe somebody came up with this conjecture. Maybe this is a non-native English speaker, and they're just learning the language, so they learn the months of the year January, February, March, and April, and they're noticing, maybe looking for some patterns here to try to see how these names are constructed, and they may notice that January and February both have a Y, March and April do not have Ys, but they do have Rs, so maybe their guess is that every month's name in English contains either Y or R. Well, if we wanted to prove that that's not true, we would need to come up with an example that meets all the conditions of this conjecture. So it would need to be this first part. It would have to be the name in English of a month, and then we need to contradict the conclusion of this conjecture. We need to come up with an example that does not contain Y and does not contain R. All right, so you can probably think of your own examples here, but all we would need is one to show that this is a false statement. So maybe you come up with the month June. That would be a good counterexample. What about all numbers that are divisible by 5 are divisible by 10? So a counterexample would need to be something that is divisible by 5, but contradicts this last part. It has to not be divisible by 10. Okay, so quick review, divisible means like goes evenly into with no remainder. So, for example, the number 15 is a number that is divisible by 5, but is not divisible by 10. So that would disprove this statement. And then finally, what about the conjecture, all prime numbers are odd? So if we're looking for a counterexample, it would need to be a prime number, and it would need to be one that is not odd, or in other words, that is even. All right, so prime numbers are numbers that are only divisible by themselves and also the number 1. So for example, 2 is prime, since only 1 and 2 divide evenly into it. 3 is prime, 5 is prime, okay, but 4 is not prime, since it's divisible by 1, 2, and 4. 9 is not prime, since it's divisible by 1, 3, and 9. And of course, there are many other examples. All right, so can you think of a prime number that is not odd? Well, in this case, there's only one counterexample. The number 2 is the only prime number that happens to be even. Okay, but that's enough. We just need one example. And you could say that this statement's close to being true, but not actually true because of the example 2. Okay, so practice this on your own. So write 2 false conjectures. All right, so I'll have you do this. And then rather than writing a counterexample for your own conjectures, why don't you do this for another classmate's? So what you'll be contributing will be the 2 false conjectures. Okay, so 2 false statements. And then try to make those general as well. I think those are going to work best, because if we're looking for counterexamples, we're trying to come up with specific examples for which that general statement is not true. And then you'll go find another classmate's conjectures and see if you can think of counterexamples to each of those statements.